Hello, Mr. Tony. So this lesson is about experimental platform usage. So the first one was general introduction. The second was the configuration part. Now, how we can use this platform. Okay. The outline of this presentation. It starts with the presentation of the experimental platform, followed by the controller design and simulation platform. Then they talked about the PSP toolbox modules, followed by the PixHawk hardware system and hardware in the loop simulation platform, and finally the sum. Okay, so the platform composition. This platform contains five components, main components, which are Simulink based controller design and simulation platform, which we are talking about MATLAB and Simulink. Okay, this is the first component. The second one is the PixHawk autopilot system as a system, which contains the hardware and some software, etc. Okay, the third one is the hardware in the loop simulation platform, which contains sim, etc. And the multi-copter hardware system. Here it is all the hardware of the multi-copter, airframe, etc., which were presented in the previous lesson. Okay, and the final component, which is the structure package. Okay, now each component will be detailed in the next slides. The first slide, which is about the Simulink based controller design and simulation platform, the first one. We mean by it the MATLAB and Simulink with fight gear, simulation PSP toolbox, etc. This softwares. It offers a high fidelity nonlinear model, modular controller design, real-time 3D display for the flight status, automatic code generation and upload function. As you can see, the different tools which are here, and they are already presented in the previous lesson. PixHawk target blocks, as you can see here, which is presented in the PSP toolbox. This one, you can see the different models of the hardware in the software. The model of the hardware in the software. Yeah. This one we will see it later. This is the one simulation system in the loop simulation. Okay, platform composition. Okay, the second part, which is a hardware in the loop simulation platform, which contains the copter sim software tool, which is a real-time motion simulation software, and 3D display, which is used to display the multi-copter status, position, etc. in the space. Okay, so the hardware in the loop simulation contains copter sim, 3D display, QGC, and these hardware. Okay. The third component is the PixHawk autopilot system, which contains the hardware, the controller, the transmitter, the receiver, the battery, and the autopilot, of course, with the QGC in the PC. Okay, the PixHawk RC controller, yes, a micro USB cable, and QGC, yes. The fourth component, which is the multi-copter hardware system, which contains the airframe system, the propulsion system, and the external sensors with test stands. Okay. which are shown in these pictures. And finally, the first component, which is a textbook, experiment, and instructor, source code examples, and video tutorials. This one I didn't find it. Okay. Platform advantage. The advantage from this platform is that it provides interfaces for multi-copter controller design in MATLAB and Simulink. Okay, so it provides the interfaces where you can replace the model of a certain system with its corresponding hardware. So, you know. Okay, readers, beginners or students or engineers can develop a rapid design using a system in the loop system, software in the loop system, simulation, and verify the control algorithms by system in the loop simulation. Yes. Platform also provides a code generation function to generate Simulink controllers to C++ code. This platform also provides a hardware in the loop simulation platform for preliminary simulation tests on a Pixhawk autopilot system that may help in eliminating potential problems that may exist in flight tests. Yes. After all the tests are completed, indoor and outdoor flight tests can be carried out by assembling the Pixhawk autopilot onto a real multi-copter hardware system. The performance of the designed controllers can be evaluated through experimental tests. Okay, this book provides a high-fidelity simulation environment based on Simulink, based on flight gear. The main source code can be found here in this location. I suppose you already downloaded this file, this folder. Okay. When you go to this directory, you will find this file. When you click on it, it is a Simulink file. When you click on it, you open Simulink interface. When you open a Simulink interface, you will find the system in the loop simulation. The software in the loop simulation example here. As you can see, the controller and the multi-copter model and flight gear interface. So this simulates the model. This one simulates the space or the outdoor environment. This one simulates the model or the multi-copter itself, and this one the controller. Here we control the multi-copter in the space, in the open space. Okay. Now we will see the details of each part or each component, starting by the controller. As shown in the left figure, this figure, it shows the internal structure of the controller subsystem. This controller, when we double click on it, you will find the components of this subsystem. This is the whole system. And when we click on it, on the controller, we go to the controller subsystem. As shown in this figure, this example shows a simple attitude controller. So it controls the attitude for pitch and roll and angles. The controller receives the control signals from the RC transmitter. Okay, and controls the multi-copters to achieve. So he receives the RC from the RC transmitter. He receives signals, and he controls the multi-copter to achieve the desired pitch and roll angles. Okay, as you can see here, there are some inputs here for the controller in order to use them for the control of the multi-copter. How what is there inside? It is shown here. Different channels, the channels of the RC controller, RC transmitter, and the phi theta, which are used as an input. Then the controller we will go in the details. Okay, the input interfaces module. The input interfaces module, this module, okay, receives the RC transmitter signals and the multicopter state estimation signals. Okay, then to these inputs they go to the RC signal process, which are radio control signal process. The RC signal process module maps the 5-channel signals of the RC transmitters to the desired roll and pitch and angle values. Okay, so he maps this subsystem, find the corresponding roll and pitch angles for related to the input which are the RC signal process. The RC signal process, which we can tune them, or which are manually can be controlled. It is our command. Okay, then we go to the third subsystem component of the subsystem from the whole system. Okay, this is the third component. It is the attitude controller. The attitude controller module computes the desired force. So here, what we find the desired roll and pitch angle. Then this one, the attitude controller, compute the desired force and torque values to control the multicopter to the desired attitude. Okay, so here we have the angle, and here we get the desired force and torque. Then we go to the fourth component, which is motor control signal computation. The motor control signal computation module, this module, maps the force and the torque values to the control signals ranging from so here we get the values of the force and the torque, and from here the output of this component is the control signals ranging from 1000 to 2000 for the 4 motors. So these these control signals are sent to the output interfaces. The output interfaces module fills the remaining 4-dimensional control signals and generates an 8-dimensional pulse width modulation PWM signal. There are 8 PWM pulse width modulation output ports on PIC's hub, ranging from 1000 to 2000. As you can see here, it is used to fills the remaining 4-dimensional control signals to generate the 8-dimensional pulse width modulation signal. This 8-dimensional pulse width modulation signal is the output of the controller. The output of the controller is the input for this subsystem, which is the multicopter model. So the controller sends to the multicopter model the pulse width modulation signal. The pulse width modulation signal for each motor of the drone or of the multicopter to control the velocity and therefore the force and the torque, etc. Yes. Now we go to the second subsystem, which is the multicopter model. As can be seen here, we can see here the internal structure of the multicopter model subsystem. It contains the battery model, fault model, rigid body kinematic model, force and moment model, motor model, environment model, and the output interface model. Let's see them. First, the inputs. The inputs. What is the inputs? What are the inputs? The inputs are the motor pulse width module control signals, which are obtained from the controller, as I said before. The outputs. What are the outputs from this multicopter model? Are the flight state and sensor signals. So when we this is our multicopter. When we give it the command or the pulse width modulation to control signals, which control the torque and the force of the motor, what we need as an output, we need the flight state and the sensors signals. Okay, these states and signals are then going out from this subsystem and going into the flight gear interface to see how it flow in the space inside this tool or subsystem. Okay, let's go back to this subsystem. We start by the motor model. The motor model, where is it? It is here. The motor model module, it simulates the motor dynamics. Dynamics meaning there is a force. Okay, as we studied previously. Yeah, dynamics. There is a force. Rules of Newton, if you remember. Okay, then we go to the force and moment model this one. So this one simulates the dynamics, this one of the motor, this one simulates all external forces and moments acting on the body, such as the propeller thrust, fuselage aerodynamics, gravity, and ground supporting force. Yes. And then we go to the rigid body kinematic model. Here the kinematics, so the study will be about the velocity, acceleration, etc. Not with respect to the force and the torque, etc. Okay, it calculates. Where is it? Here it is. Here. This is this component. It calculates the vehicle kinematics of the multicopter, such as speed, position, attitude, but not force. Not the force. The force it belongs to the dynamic. Okay. Okay. Let's move on. Let's move on to the environment model. The environment model. This model module it calculates the environmental data, such as gravitational acceleration, air density, wind disturbances, and geomagnetic field. Then we go to the fault model, this one. The fault module, this component, it is mainly used to inject model uncertainties. Uncertainties in the model here, we need to inject the fault, because practically when you give a control signal to for the multicopter model, practically there is heat, there is some factors which will affect the operation of this subsystem. So in order to model this introduced ambiguity in the subsystems, we use this model as to introduce the fault model. Fault model, it is used to inject the model uncertainties related to mass and moment of inertia, as well as faults. So now battery model. Battery model module, it simulates the discharge process of the battery. This one. And finally, the output interface model module. This module packs the output signals in the desired format. Okay, in the desired format to switch the flight gear interface. Now we go to the flight gear interface. As we can see here, the flight gear interface subsystem has 3 input ports representing the multicopter position, Euler angles, and motor pulse width modulation signals, respectively. This subsystem sends multicopter flights state information to flight gear to observe the flight attitude and trajectory of the multicopter in 3D scene. So here we can view it as the outdoor space, simulation of the outdoor space. As you can see in this figure, a quadcopter in flight gear. So the effects. Now, the double clicking on the flight gear F, this one, shortcut on the desktop to open flight gear. Then click Run button on the Simulink toolbar to run the concept, the file which was presented during previously. Then the multicopter tasks. The multicopter takes off vertically from the ground. You can slide the slider modules in Simulink to simulate control the roll, pitch, yaw, throttle channels of the controller with the RC system. So here in this slide, the author of this PowerPoint shows you how to execute this software in the loop simulation by following this three simple procedures. Okay, you start by flight gear, then you go to Simulink, then you do the controlling stuff in Simulink, and you see what you have controlled or the effect of your command in flight gear. Okay. Now we move to the PSP toolbox. The figure below shows the relationship among the PSP toolbox, the PX4 software, and the PixHawk hardware. PixHawk Pilot Support Package PSP toolbox is a Simulink toolbox officially released by MathWorks, which is the company responsible for MATLAB. This toolbox can use the embedded coder in Simulink to automatically compile and deploy Simulink model autopilot algorithms to PixHawk hardware system. So this is the PX4 software. As you can see here, we have MATLAB Simulink. Then this Simulink control algorithm are co-generated to the PSP toolbox. This is the PSP toolbox. This is PX4 software, and this is using the PSP toolbox in Simulink. We do the co-generation of the Simulink generated PX4 Simulink app. The expansion is PX4. Then this code will be utilized with the OLRB message pool. This module has interaction with Kalman filter, attitude controller, position controller, and motor control. With, of course, the motor control is related to hardware interfaces. Well, these things will be much more described or and will be much more presented in the next slides, explained in next slides. The main function. The toolbox can simulate and test different multicopter models and flight control algorithms in Simulink, and then automatically deploy the algorithms to the PixHawk autopilot. The toolbox provides many practical examples, including LED control, RC data process, and attitude controller. The toolbox also provides many different mini interface modules to access the PixHawk hardware and software components. It automatically records flight data from sensors, actuators, and controllers deployed by themselves. It can subscribe and publish UORB topics messages. All messages in the PX4 autopilot software are temporarily stored in the UORB topic message pool. The subscription function can read topics of interest from the message pool, and the publishing function can publish specific topics to the message pool for other modules. So it is all related to this UORB message pool, as you can see here. This is where inside the PX4 software. Okay. Yes. Relationship with the PX system. The structure of a the structure of a autopilot system includes two parts: the hardware, similar to the computer software, and PX4 software, similar to the operating system, and the applications on a computer. The PX4 software system can be further divided into several small modules, which run independently in parallel multi-thread. Each module exchanges data with other modules through the UORB messages. Saying this is more explaining this figure, this one, as I said before. Okay. After the algorithm code is generated by the PSP toolbox, it is embedded into the PX4 software system. This will not affect the operation of the native control modules in the PX4 software. Instead, a new independent module named PX4 Simulink App will be created to run in parallel with other modules. Native modules in the PX4 software may access the same hardware outputs as the generated PX4 Simulink App module, which may cause read and write conflicts, because read and write conflict is because of the old and the new generated code. Therefore, in the 1K installation script, the hardware output accessing codes of the PX4 native modules have to be blocked. This will ensure that only the new the PX4 Simulink App module can send motor control signals. Now we will move to the process to generate code. Wait a minute, 1 minute. Okay. The process to generate a code. So the PSP toolbox generates the PSP toolbox in Simulink here. Generates the C++ code from the control algorithm designed in Simulink. Then the obtained algorithm code is imported into the PX4 source code to generate this file, PX4 Simulink App, this file, independent of other modules, independent of these modules. Okay, the PSP toolbox calls the compiling toolchain. Then the PSP toolbox, this toolbox called the compiling toolchain, this one, which I already presented in previous lesson, to compile all the code into the .px4 extension. Okay, here, firmware file, similar to a software installation package in Windows. Upload then the next step is upload the obtained firmware file to the PX hardware using this injecting tools. Okay. Then the PXHawk autopilot can execute the PX4 software with the generated algorithm code. This is the process. So this is how it works inside. Now, advanced extensions features. Note, another feasible way is to block the module in the startup script. This one. Okay. Now, the generated Simulink code can also be used to replace some of the native modules, such as sensors, filters, attitude controllers, etc. Here, what we want to say is that some of these modules, of the modules here, can be replaced by another modules in Simulink, because another modules in Simulink, meaning that they will be co-generated to be in this module, and when a certain module in the PX4 software is deactivated or blocked, the block presented in this file will replace it, will be the replacement. Okay, where we were okay, we were here. Yeah. For example, if readers want to use Simulink to replace the attitude filter module, input the sensor data, output filtered attitude data of the PX4 software, they should manually block this publishing code of the vehicle attitude message in the position and attitude estimators module. The detailed steps are described in this described next. Open the how you can block this code, because you will use it in Simulink. You can open this file corresponding to the code of the extended Kalman filter module. You search for the text, this one, and comment out the lines containing publish and the attribute, and replace them with unused. The unused is used to suppress the warning of variable not used of compiler. Create Simulink controller to publish vehicle attitude message with URB PSP modules. This is how in this lesson it describes how you use the platform which was configured in the previous lesson. Okay, so it's not mainly an experiment. The experiment will follow in next. Okay, Simulink picks how targets blocks. Here, this image shows the Simulink the target blocks of the PSP toolbox. As you can see here, there is RDC and serial, etc. Now there is also in this figure the interfaces of sensors and actuators, which are seen here, which are being seen here. Okay. Then we go to the Simulink picks how target blocks. The official examples and manual of the PSP toolbox, as you can are shown in this file, which I suppose you have already downloaded this file. The PSP toolbox also provides many examples. See this folder with an official manual for readers to be quickly familiar with the functions and usage methods of PSP toolbox. Well, I advise you to follow the experiment, and during the experiment you can practice the usage of the platform. Okay. Now we go to the important part, because it is this one present the modules in the PSP toolbox. It is as dictionary if you want. Okay, we start the first module, which is the pulse width modulation output module. This one. It is used to send pulse width modulation signals to PX4 input-output ports to control the motor. The pulse width modulation updates frequency and the number of output channels can be configured in the setting box, as you can see here. These are modules presented in the PSP toolbox in Simulink. Okay, now we move to the second module, which is RC input module. It is convenient to select RC channels and other information to be used by Simulink. The definition and the application of each option can be viewed by clicking the help or by consulting the official PDF document. The PSP toolbox also provides an example in this directory to show how to use this module. Okay, now we go to another module, which is buzzer module. Buzzer module and its parameters setting box, as you can see here. It is used when the buzzer beep is required to make a warning sound. There is an example in this directory for detailed information. RGB LED module. This module can control the blinking mode of color of the LED on PixHawk, the module receives two inputs, namely mode and color, representing the mode and the color of the LED. The PSP toolbox provides an example in this directory to study this module, as you can see in this picture. Another module is sensor combination module. This module also in the PSP toolbox I said previously in Simulink. This module can access the sensor data available in the PixHawk autopilot, which can then be used for controller design in Simulink. The available sensor data include magnetometers, accelerometers, gyroscopes, barometers, and timestamps. The PSP toolbox also provides an example in this directory, as you can see in this figure. Attitude data module provides the interface access the attitude to the attitude estimator using Euler angles and of the Euler angles and quaternion. The PSP toolbox also provides an example in this directory to study the module, where this module will be used in the experiments, in the following experiments for the upcoming experiments, in the upcoming lessons. Okay, modules in PSP toolbox. Here the GPS data module. It can be used to access the PixHawk GPS data, which are achieved by subscribing to the UORB topic vehicle GPS letters. Therefore, in practical operation, it is necessary to ensure that the GPS module is inserted into the PixHawk hardware and then works. Okay, here as a note, the PSP toolbox also provides an example. You can see this file directory to study this module. Now we move to this module, which is battery data module. It can be used to obtain the real-time status of the battery. It is implemented by subscribing to the UORB topic battery status. Therefore, in practical operation, it is necessary to ensure that the power module is inserted into the PixHawk hardware and then works correctly, as shown in this picture. Now we go to this module, which is UORB modules, these modules are presented in left figure, as you can see here. UORB read and write modules. UORB write modules parameters to tick box. This one, okay, which are used these parameters, modules are used to read or write UORB messages from the PX4 autopilot software. All the UORB messages topics supported by the PX4 autopilot and are listed in the this directory of the software package installation directory. The default directory is this one by default. Double click the UORB right, this one, module in the lower left figure, this one, UORB right. Yeah. Okay, the lower left figure. Then the obtained parameter settings box of the UORB right module is presented in lower figure right, this one, to obtain this window. Okay, where the UORB topic name and the messages, the message variables to be sent to can be configured. Here you can configure to the messages that you will send using this module. Clicking the open dot message, this one, button in the upper right figure here. Yields the content of the selected dot message. The content of the message here, as you can see here, and clicking the open dot message folder. When you click the folder, click on the open the folder, you go to the directory. Yields the list of all supported UORB messages. See the lower right, this one. Okay, now we go to. Okay, as you can see here, all the modules, presented modules such as pulse width modulation, output, RGB LED, etc., mentioned in this section are implemented as the underlying code by reading and writing UORB messages. Theoretically, by using the UORB read and write modules, all messages and intermediate variables used in the PX4 autopilot can be accessed by Simulink. This simplifies the implementation of more advanced functions for controller design. The PSP toolbox also provides two examples. You can see this in this directory and this directory to study these modules. Well, concerning this remark, as you can see here, there are two modules for URB rights, but this one has an extension DAEI. Here, as you can see, there are two modules. The suffix DAI allows sending extended messages such as actuator controls 0 based on URB message based class such as actuator controls. So it provides an extension of the module. URB write advanced module, as you can see, message ID is the name of the message file, and this one also. Also to write advanced DI module, messages ID can be set different from name of the dot message file. So this is the difference between them. This suffix gives you more extended messages. Modules in PSP toolbox in the same part we are here. For the sake of convenience for controller parameter tuning in flight test, the PSP toolbox also provides interfaces to access the peaks for internal parameters. In this way, the parameter of the controller generated by Simulink can be tuned online in the GCS software. Instead of modifying the controller parameters in Simulink, generated code, and uploading the firmware file again. An example of how to access the peaks for internal parameters is presented in this file. You can just open it. It is just a Simulink file and run it here, as you can see. Okay. Peaks for internal parameters access is realized by using the function this one, which needs to be called in Simulink initialization function. Click sample to click by clicking sample, then model properties, then call bugs, then init initial function in Simulink menu bar. For the example shown in the lower left figure here, the corresponding parameter initialization script is shown in the figure on the lower right. Now for the code generation, configuration, etc. Here it is more practical, so it will need to be done in, as I can see in in TeamViewer. As you can see, it is step by step. It is more practical. Okay, you can see it is they are all steps. Yeah. So thank you for your listening, Mr. Tom. Hello. For this lesson, the fourth lesson, it presents the experimental process. So the first one was a general introduction. The second present the configuration of the platform. The third was about the usage of the platform, and this one is a very short lesson about the process. Okay. It starts by the experimental process, and this lesson is about the experimental process. So It is mainly in this part. It is focused on this section. Then the lesson presents an experimental procedure for LED control experiment, and another experimental procedure for the attitude control experiment, and finally the summary. So as you can see here, these two sections mainly they will be practical because they are step by step procedures for an objective. Yeah, will be done in TeamViewer if you like. Then we start by at the beginning we start by the experimental process. The experimental courses include propulsion system design, modeling, filtering, control, and decision making, as you can see here. Here, as I described in the first lesson, the introduction. Sorry. Each experimental course includes 3 step-by-step experiments. It means the basic experiment, an analysis experiment, and design experiment. I already said that. It is just a repetition. The progressive route for the 8 experiments as is shown here, as you can see. It follows this one, then this one, then this, then this. It starts by design and modeling, then estimation of experiment, then control, then decision making. The basic experiments in each experiment there are the basic and the analysis and design experiments. The basic you need to open a given code example, read it, run it, and observe it, record it, and analyze the results. The second type of experiment, it is by modifying the given code example and then run it to collect and analyze the data. Then the third part, which is the design experiment, it is based on the above two experiments, but completing a given independent task. For the basic experiments and the analysis experiments, this book provides source code examples to ensure that all readers can complete them easily. Through the above two experiments, the readers will acquire a deep understanding of the theoretical and practical methods. In design experiments, the readers will independently design and verify algorithms by referring to the code examples offered in basic experiments and analysis experiments. The 3 step-by-step experiments constitute a learning ladder for shallow to deep, which is convenient for readers to reach the final experimental goals. It is just this paragraph is just explaining or describing the importance of this experiment. It is building step by step. Okay, each experiment generally includes the following 3 phases. So it is Simulink based algorithm because it is a software in the loop simulation phase, and a hardware in the loop simulation phase, and the flight test phase. As you can see here, software in the loop simulation phase, the first phase, we need MATLAB Simulink with flight gear connected to each other. They are both softwares, not hardware. So therefore it is software in the loop. Then the second phase, there is hardware in the loop. You can see there is Pixhawk autopilot system, there is a hardware component connected to the PC, ground computer. This ground computer has softwares. The softwares so it is mixed hardware and software. Therefore, it is hardware in the loop simulation phase. Flight test phase, it is completely testing experimental procedures, steps or instructions. Okay, considering the possible risk, this is what I was talking about in the first lesson. Considering the possible risk, the practical flights may not be included in the experimental content. So mainly it is simulation-based algorithm, SIL or HIL. Okay. Simulink, starting by the first phase, which is software in the loop simulation. The entire phase is performed in MATLAB. Yeah, it is more if describing what I have already said. Environment. Readers can design control algorithms in Simulink based on the given multi-captured simulation model. The input and output ports of the designed controller and the multi-capture simulation model should be correctly connected to ensure that the data transmission is consistent with the real multi-capture control system. Similar to a real multi-capture system, the multi-capture simulation model sends sensor data or estimated states to the controller, and the controller sends back to the motor. The motor ports with modulation control signals to the multi-capture simulation model. This sets of closed loop hard in the loop simulation software. This system not hard in the loop, it is here SIL, software in the loop. Yes, in this phase, readers can analyze. Okay, this one software in the loop. Yeah. In this phase, readers can analyze the control performance by observing the simulation results, then modifying them, the controller, or redesign it according to the desired performance requirements. Now we go to the second phase, which is hardware in the loop simulation phase. In this phase, readers will import the multi-capture model from the Simulink, okay, to CopterSim. Upload the control algorithms from Simulink to a real PixHawk with the code generation technology, and replace the Simulink virtual data connection. So we replace the Simulink virtual data connection with a real USB cable. CopterSim sends sensor data, example accelerometer, to the PixHawk system, which is a hardware, via USB cable. The PX4 autopilot software in the PixHawk system filters the sensor data and estimates the multi-capture states. Next, it sends the estimated multi-capture state to the designed controller via the internal UORB message bus. Then the controller computes the motor ports with modulation control signals and sends them back to the copter sim via the USB cable to establish a closed loop hard in the loop simulation system. So detailed process is described here for this phase. Detailed steps are here. Okay, compared with the system in the loop simulation system, the multi-capture simulation model in the copter sim is running with the same clock speed in the real world to ensure the real-time requirements, and the control algorithms are running in a real embedded system, namely the PixHawk autopilot, which is better emulates a practical multi-capture system. Note that the data transmission delay is inevitable in a real communication system, and the operating environments of the simulation model, as well as the control algorithms in the hardware in the loop simulation system, are difficult to be consistent with the software in the loop simulation system. Therefore, the controller parameters may need to be slightly tuned based on the simulation results. In any case, this is consistent with the system development process of a real multi-capture system. Flight test phase. In this phase, the multi-capture simulation model in CopterSim is further replaced with a real multi-capture hardware system. The sensor data are replaced with signals from real sensors chips by sensing the multi-capture motion and states, and the control signals are directly output to the picks how input-output ports to control the motors. Note that it is difficult to ensure that the simulation model used in both SIL and HIL is identical to the dynamics of a real multi-copter system. Consequently, the controller parameters may need further slight tuning according to the experimental results. Experimental objectives. Now the objectives here are to use two channels from channel 1 to channel 5 of the radio controller transmitter to control the LED. Now this is for the experiments. So he starts by stating the objectives and then he follows the design procedures. Okay, the objectives and the procedures will be done in TeamViewer because the procedures they are step by step. It is step by step procedures, practical procedures, which should be done by hand. Yes, as you can see. 4, 1, 2, 3. This is the results. Yeah. Okay. Thank you for your listening, and I hope this gives an idea about the simulation procedures. However, for the practical side, we need to follow step by step according to the stated instructions. Thank you.